Can I start? Okay. So hello everybody, I'm Elisa BORTOLAS from the University of Padova, and today I'm going to tell you about massive black hole binaries and their coevolution with their host galaxies. So first of all, from the lambda CDM cosmological model, we think that galaxies aggregate hierarchically from smaller structures and subgalactic units. And also observations witness that most galaxies host a supermassive black hole inside their nucleus, and this seems to be true even at high redshift. So if we put together these two facts, we expect a lot of supermassive black hole binary systems to form in the merger remnants. And these black hole binaries are really important because they are expected to reach the coalescence in a burst of gravitational waves. These low-frequency gravitational waves are expected to be visible by future observatories, such as the Elisa mission that is planned to be in the sky in like 15 years, and also by the pulsar timing array, hopefully in the future. And the detection of such gravitational waves is going to be really important if we want to understand better the origin of such supermassive black holes, because their origin is already really mysterious, and also if we want to check if the hierarchical merger paradigm is true or not. But how does a massive black hole binary evolve? So first of all, the two galaxies merge, and the two supermassive black holes, they spiral inside the center of the merger remnant due to the effect of dynamical friction, a sort of gravitational drag. And when they form a binary system, a bound binary system, if the system is gas-free, meaning like if we think about ellipticals, the two black holes are expected to shrink mainly due to the effect of interacting stars. So each star that interacts with the binary is expected to be literally ejected from the system, and the binary loses energy in the interaction and it shrinks. And this hopefully will continue down to a separation of a milliparsec, more or less, and at these small separations, gravitational waves start to be efficient in shrinking the binary, and they will lead to the final coalescence. But it is crucial to understand whether this second step is efficient enough to bring the binary to such a small separation, because otherwise we wouldn't see any black hole binary to merge within the Hubble time. So it's something we are interested in. And actually, the very first simulations of black hole binaries evolving in spherical systems seem to hint that the binaries would never reach this gravitational wave emission stage, because once the first stars are depleted from the central regions, then a void basically is created in the center of the galaxy, and no more stars go down to the center, and the binary has no way to shrink further, right? But these seem to be just an effect of the oversimplified assumption of sphericity, because if you think about a more general system that is expected to be triaxial, so not perfectly spherical, the orbits are much more complicated, and the large-scale torques make stars to go from the very large-scale structure down to the center, and this is a continuous process that makes the binary continuously shrink and reach the coalescence. And this is a good news if you want to observe gravitational wave emissions, because basically perfect sphericity doesn't exist in nature, right? All systems are deviate at least a bit from sphericity. So we understood that the remnant, the shape of the remnant is really important for the binary shrinking. And it is reasonable that such shape will depend on things like the merger of orbit of the two galaxies that form the remnant, and also the properties of the two galaxies themselves, for instance, their density profile, their shape, their mass ratio. And also it turns out, I will show you, that even the presence of a massive black hole in the nucleus of one or the two galaxies can change the the structure of the host galaxies. So we asked ourselves how the merger properties can influence the shape of the merger remnant that in turn influences the binary shrinking rate. And what we did is that we tackled this problem via a suite of direct summation and body simulations. We limited ourselves just to the Newtonian gravity because we don't want to reach the gravitational wave emission regime. We basically simulated mergers of equal mass spherical galaxies, and we modeled each galaxy has a Denman density profile, that is a density profile that well matches the observations of ellipticals and spherical galaxy bulges. And we explored the space of parameters by varying the eccentricity of the merger, so from more circular mergers with E equal 0.5 to more radial mergers, and we also varied the inner density slope of the two merging galaxies from gamma equal 0.5, that means that the system is shallower, to a more cast system with gamma 1.5. And these 3×3 9 configurations, we tried all of them, but including or not including a massive black hole in the center of the two merging galaxies that leads to the formation of a massive black hole binary in the remnant. And here I'm actually showing the outcome of two simulations. On the left you see the same simulation without the black holes, and on the right hand you see the simulation when the two black holes, the red cross, are included in the systems. And the top panel shows basically the orbital plane, and this is the orthogonal projection. So you see the merger, and then in the end you end up with a system. And I already want to show you that you can see a difference, because if you look at the left, you can see kind of a bar-like structure in the center that rotates, while on the right you don't see it, right? And so, before moving to the description of my results, I want to introduce you, if you don't already know it, to the triaxiality parameter. So we are interested in the shape of these galaxies, right? And we want to find the ellipse that best describes, the ellipsoid, sorry, that best describes at each different scale the shape of our merger remnant. And this can be characterized by three different axes. We call them A, B, and C, and they follow this relation. And from this, we define this triaxiality parameter like this. And what does it mean? It means that if the system is a disk-like structure, we call them oblate system, meaning that the two longer axes are equal and you see kind of a pillow. On the other hand, if the two shorter axes are equal, basically you end up with a prolate system that has a ballet-like structure, and the triaxiality parameter, you can work it out, is equal to 1. But what we wish most is to find the systems that have a t equal to 0.5, meaning that each of these three axes is different from the others, because this will ensure better the binary shrinking. And so here I show you the outcome of my simulation. So each different column shows systems with the different concentration, from low concentration system to high concentration system. And also from each row shows mergers that are from more circular to more radial. And in each panel you see two curves. The black one indicates a merger that includes a massive black hole binary in the center of the remnant, while the red curve indicates a system without any massive black hole in the center. And I show these curves as a function of the enclosed stellar mass. So here, basically, you see the influence radius of the binary, if it is present, while this side shows the very large scale structure of the system. And what do we find out? What is the dependence of this triaxiality parameter? So the first thing we can notice is that at very small scale, the system, especially if it hosts a massive black hole binary, is generally maximally triaxial. So you see these points here, right? And also, a thing that turns out is that we have a striking difference, especially in some cases, when the binary is not present and when it is present instead. So when the binary is absent, the system is generally prolate, so a ballet-like structure, and it is generally deviates more from sphericity. While if we include a binary in the same system, the system becomes more oblate, more kind of a disk, axisymmetric structure. And also I want you to notice that it's striking that basically if there is a binary in the center of the system is never prolate. So T is generally maximum 0.5. And this is kind of an interesting result, in my opinion. And also, as I showed you before, if there is no binary in the center of the system, we find the kind of rotating bar-like structures that can kind of form in a really few cases if the binary is present. And yeah, I already showed you the difference between the two, right? Okay, but what drives this difference between the two cases is that the binary itself, or even if we include just one single massive black hole, we still see the same effect. So we made this test for one particular case, and here I show you again the triaxiality parameter as a function of the enclosed stellar mass. When no black hole is present, you have this line. When a binary is present, you have the black line, but when just one black hole is present, you see we can get basically the same trend. So even a single massive black hole leads the system toward diskiness, toward oblateness. And this basically means that it's not the effect of a slingshot interactions of the binary with the stars that leads this difference, but instead it's rather the potential of the massive central object. And so we dig a little bit into the literature and we try to understand why this happens. And here I sketch a really simple and simplified image of a stellar orbit when a massive black hole is not present in the system. And we think about the same orbit and we put a massive black hole in the system. Basically, this black hole scatters the star and it changes its orbit, and it turns out that the massive black hole in the center of the system acts as a scattering center for the stars, and it renders regular orbits chaotic. And this happens far beyond the influence radius of the massive black hole or black hole binary. And this means we will have some observational features to look at, and it's really interesting news, in my opinion. But now, let's see how the shape of the system, so the triaxiality and axis ratios, vary as a function, for instance, of the eccentricity of the merger itself. So on the left, you see the case when the binary is present, on the right, when the binary is not included. And what it turns out in almost all cases is that if the merger is more radial, so the eccentricity is higher, B over A gets smaller, and the system becomes more either triaxial, if there is the binary, or even more prolate, ballet-like structure. And this makes sense, because if you merge two systems like this, you expect to have a ballet-like system, right? And on the other hand, if the merger is more circular, we end up with more disk-like structures, because if you merge two systems like this, you expect a more disk structure. It's something, in my opinion, makes sense. I hope also in yours. And also we studied the dependency of the shape of the merger remnant on the steepness of the density profile of the merging galaxies. And what we found out is also kind of similar when the binary is present and when it's not. Also the differences are enhanced when the binary is not present. So basically, if the systems are more concentrated, we tend to go to a system that is more oblate, less prolate. And instead, if we start from a shallower density models, we end up with systems that can be more prolate, and I think that is because it's easier to change strongly the shape of a system that has a lower central concentration. But now, down to the binary hardening rate, that is the main subject of my talk. How does it change depending on all these properties? So here in this lower plot, I show you the 1 over the semi-major axis of the binary that is shrinking for different merger properties. And in the top panel, basically you see the first derivative of the time of the quantity below, and this is basically how fast the binary loses its energy. And what turns out is that if the system is low concentration, the hardening, the shrinking is less efficient, while if we make the system more concentrated in the inner parts, the hardening is boosted. And this makes sense because if we have more stars in the center, the binary has more stars to interact with. But then, what if we change the eccentricity of the merger? Here you see that if we have different eccentricities, as I showed you before, the triaxiality parameter of the system changes, right? But on the other hand, the shrinking rate, this hardening rate parameter, is basically constant independently on the fact that we have this variation. It doesn't depend on the eccentricity. So basically there is no clear correlation between the triaxiality and the hardening rate of the binary. And this might be due to the fact that the system is almost maximally triaxial in the very center, or also to the fact that the outside of the system is generally quite similar in all our cases. And given this, we can think that there is a kind of magic number, maybe, that doesn't require the effect of the merger. We can kind of guess how is the hardening rate of a binary, and independently of the remnant properties, but just caring about the cuspiness of the model. And obviously, we don't want spherical systems, as I told you before. And also, we studied the rotation of the net rotation of this model. Again, I showed you the rotation as a function of the concentration parameter and of the eccentricity of the merger. And what happens basically is it, again, if the binary is included, so you see these black lines, we have a difference compared if the binary is not included. So the inner parts of the model rotate just if the binary is included. Not even in all cases, but let's say in most cases. While the rotation is basically really, really suppressed if the binary is not included in the system. And also what it turns out, and it makes sense, is that if the merger has more orbital angular momentum, the outside part of the system rotate more. And I also want to point out that the outskirt of the system seems to absorb most of the rotation of the merger. And these differences, by the way, the differences we see between the two different runs, extend far beyond the influence radius of the binary again. So it's not just an effect of the potential, I would say. It might be an effect of the potential, but it's something that extends beyond and can be observed. So why we have this difference? I made this picture that, in my opinion, makes sense. So if we think about a star on a circular orbit around the binary, it will go around happily, and it won't really interact with it because it stays far away from it. While if we think about a star on a really eccentric orbit, the eccentric orbit makes the star interact with the binary, and it will be at some point ejected. So basically, we lose all stars on radial orbits, and we keep the stars on with more rotation if the binary is present. And also, we wanted to study the escapers. So how many escapers are produced in different cases if the system hosts a binary and if not. And you see from these curves, basically, oh sorry, I went too fast, that the black lines basically show you systems without a binary in the center, while, sorry, with the binary in the center, while the red lines show you the systems without the binary. And after the merger is completed, that is basically the division point here, if the binary is not present, or even if only a single black hole is not present, no more escapers are produced from the system. While if you put a massive black hole binary in the system, the binary continuously ejects stars from the system, and the escapers are continuously produced and can be observed as hypervelocity stars, hopefully. And so this was my last slide, and here are my conclusion. The important points are like we found an interesting difference in the shape of the merger remnant if you put a massive black hole or a massive black hole binary in the center of the system. And these differences turn out to be true even in the rotation curve of the merger remnant. And these differences appear far beyond the influence sphere of the massive black hole binary. And a second important point I want you to take away is that there is no obvious link between the hardening, the shrinking rate of the binary, and the geometry of the system, at least in my simulations. And this might hint to the presence of a general recipe we can use for the hardening rate of the binaries. Thank you for your attention.